And welcome to lesson 20-2. In lesson 20-1, we unpacked the Pythagorean theorem, what most people refer to as a squared plus b squared equals c squared. And we used some similar triangles to prove that the Pythagorean theorem was true. We observed some properties of some very important quadrilaterals. And now we are going to uncover the converse of the Pythagorean theorem and what discoveries it leads us to. So before we go any further, let's take a look at our learning targets. So we've already proved the theorem, the Pythagorean theorem, so now we're going to use the converse of the Pythagorean theorem to solve problems. So remember, converse is when we switch the two parts of a conditional statement. So A being the hypothesis, B being the conclusion, we're now going to swap B and A to see what new discoveries it has for us. Well, once we figure out the converse of the Pythagorean theorem to solve problems, we are going to develop and apply what's known as Pythagorean inequalities. Remember, an inequality is when something is not necessarily equal to. It's unequal, not equal. And so we're going to look at what it means for the Pythagorean theorem when it doesn't necessarily equal c squared. So we are going to start today by chunking item 1A and B. So if you would take a moment to work on 1A and B before playing through the video. So one of Sarah's customers designed the kite. So we're still hanging out with the kite right here. So the customer claims that triangle QRS is a right triangle. Notice they did not actually indicate it was a right triangle by showing us typically a box, a little square is put there at that vertex to show it's a right triangle. So we don't know if it is. That's the whole point. So 1A said write the Pythagorean theorem in if-then form. And so a lot of you probably potentially wrote a squared plus b squared equals c squared. But if-then form, if a triangle is a right triangle, then the square of the length of the hypotenuse, which is c squared, is equal to the sum of the squares of the length of the legs, a squared plus b squared. So if it's a right triangle, notice here I kind of condensed it. If it's a right triangle, then this is true. Again, we only use Pythagorean theorem to solve missing sides of right triangles. So the converse of the Pythagorean theorem is also true. So we're trying to write the converse. So notice a couple things that switched here. The fact that it's a right triangle is now at the end. That's the whole point. We switch the hypothesis. The hypothesis of the theorem is that we start with a right triangle. So now that's going to be pushed to the conclusion. So if the square of the length of the longest side, and notice we call it the longest side because it's only referred to as a hypotenuse if in fact it is a right triangle. So if the square of the length of the longest side in a triangle, aka c squared, is equal to the sum of the squares of the length of the two shorter sides. And again, notice we didn't call them legs. It's only referred to as legs if we know it's a right triangle. So if that's true, then the triangle is a right triangle. AKA, if a squared plus b squared does in fact equal c squared, then it is a right triangle. So now we are going to use the converse of the Pythagorean theorem to determine whether triangle QRS is a right triangle. So we will chunk item 1C. So complete C before playing through the video. Okay, while number 2 might have seemed a bit confusing, especially when we really just implement algebra instead of using any type of numbers, let's make sure we understand what a Pythagorean triple is. Obviously, we get that word Pythagorean. And so a Pythagorean triple is a set of 3 numbers that represent the length of 3 sides that form a right triangle. So obviously, not any 3 measurements will form a right triangle to create that actual right angle and for those 2 legs to connect. So we create a right angle, and then for those 2 legs to connect with the hypotenuse. So there's not just any numbers in the world that can form a right triangle. We're actually going to observe that on 3. So a Pythagorean triple represents a set of 3 numbers that represent length of 3 sides that can form a right triangle. And your task here is to figure out that any positive whole number multiple of that triple is also a triple. So here are some common Pythagorean triples. The most common that you'll see very, very often is the 3, 4, 5 Pythagorean triple. And what that refers to is one side being a length of 3. That could be inches, feet, yards, it doesn't matter. One leg being 4 feet, inches, yards, doesn't matter. And the hypotenuse is, again, 5 inches, feet, yards, it doesn't matter. So this is the most common Pythagorean triple, because 3 squared plus 4 squared does, in fact, equal 5 squared. And so here are a couple other Pythagorean triples. Again, they represent length of the 3 sides of a right triangle. And so what we're trying to explore here with this algebra is that now if I were to take a 3, 4, 5 triangle and multiply it by a positive whole number, then I'll actually produce another Pythagorean triple. And it all goes back to our study of dilations, right? A positive whole number multiple is dilating that original Pythagorean triple. For example, I could take a 3, 4, 5 triangle and dilate it with a scale factor of 2, and I would get a 6, 8, 10. And if you were to actually use the Pythagorean theorem, you will see that 6 squared, I'll actually write it here, 6 squared plus 8 squared does in fact equal 10 squared, just like 3 squared plus 4 squared does in fact equal 5 squared. So once you learn a Pythagorean triple, any multiple of those numbers is also a Pythagorean triple. That's what this is trying to tell us here. So for a 5, 12, 13, if I knew 5, 12, 13 was a Pythagorean triple, and again, that means it represents 3 sides of a right triangle, then if I were to multiply this set times any positive whole number, that is also a Pythagorean triple. So for, like we did with 3, 4, 5, we multiplied it with a scale factor of 2, got 6, 8, 10, and again, that's a triple. So 5, 12, 13, scale factor of 2 would be 10, 24, 26, and that is also a Pythagorean triple. So any of these triples multiplied by a positive whole number creates a new triple. And it all goes back to our study of the dilation, because a dilation creates a similar figure. So if we start with a right triangle and we dilate it, we're still going to have a right triangle. Thus, if we know a Pythagorean triple and we dilate it, we're still going to have a Pythagorean triple. Now, the activity on the next page is a pretty awesome activity. Unfortunately, doing this virtually or through the computer, it doesn't really lend itself for me showing you how to use straws cut at these lengths to determine what type of triangle it is, but it would be an excellent activity on your own. I do want to point out before we jump over to how I'm going to demonstrate it here through the use of the video, the goal is on item 4, if A and B represent the legs and C represents the hypotenuse, what are the results in item 3 suggest about how A squared plus B squared compares to C squared? So the Pythagorean theorem states, if it's a right triangle, then A squared plus B squared does in fact equal C squared. But what happens when the sum of these two squares of the lengths of the legs is not equal to C squared, but rather potentially where the sum is greater than C squared, or where the sum is less than C squared? So that's what we're about to look at. So we are going to utilize a Geogebra activity, and here is the link over here for anybody that wants to actually do this on your own. Again, the goal is we know the Pythagorean theorem. If it's a right triangle, then A squared plus B squared equals C squared. And so the converse said, if A squared plus B squared does in fact equal C squared, then it is a right triangle. So we know if this is true, then we are dealing with a right triangle. So what we're going to explore using the Geogebra activity is what happens when the sum of these squares is greater than the hypotenuse squared, and what happens when the sum of the squares is less than the hypotenuse squared. So you can click on the link, but I already have it pulled up here. So notice exactly what I said. If A squared plus B squared equals C squared, then we know we have a right triangle. For example, this is one of those triples I was just referring to. This is the 3, 4, 5 triple dilated to a 6, 8, 10. But what if the Pythagorean theorem isn't true? In other words, what if a squared plus b squared is less than c squared? Or what if it's greater than c squared? What happens then? What if it's not a right triangle? What type is it? So you are encouraged to drag the vertices of the triangle to see the Pythagorean theorem relationship. Watch the angle, in this case, A or alpha, it's Greek for an angle here. What happens to the relationship if the angle is obtuse? What if the angle is acute? So here is the Pythagorean theorem, and again with question marks, because we're going to start manipulating the sides of this current right triangle. And we're proposing what happens when these lengths changes and how does it affect what type of triangle it is. So again, if a squared plus b squared does in fact equal c squared, it's a right triangle. But for example, what if I were to manipulate this such that the angle here is no longer a right angle, but it's an obtuse angle? So yes, I did actually not only change it from a right angle, but I actually shortened one of its sides. So observe when this angle is no longer a right angle, it's an obtuse angle. Look at the relationship of what happens in the Pythagorean theorem. We still have this side being 6, the length of one of our legs. And now our new leg is 2.88 approximately. And we see that it doesn't, in fact, equal 7.55 squared. It should be obvious because it's not a right triangle. So the relationship here is that the two squares, 6 squared plus 2.88 squared, these two squares added together is actually less than c squared. So is that true for all obtuse triangles? Is a squared plus b squared really less than c squared? So I'll actually manipulate this side as well. Maybe I have some unbelievers watching this. So let's make sure we keep it an obtuse angle. So I just changed this shorter leg. It was 6 here. I just altered that distance here to 3.479. And we see that same relationship. That the square of the two legs added together is still less than the hypotenuse squared. So it's a pretty safe bet. And again, I encourage you to actually go to this link on your own. If we are dealing with an obtuse triangle, and the definition of an obtuse triangle is if it has one obtuse angle. So here we have it. So if we are dealing with an obtuse triangle, then a squared plus b squared is not equal to c squared. A squared plus b squared is actually less than c squared. So a squared plus b squared is less than. So we could add the note here that this is actually an obtuse triangle, if in fact a squared plus b squared is less than c squared. Now let's do some observation when we're dealing with an acute triangle, or maybe start altering your sides such that a squared plus b squared is greater than c squared. So I'm going to manipulate this one side. If you notice the switch there, notice the inequality was less than. I'll point that out right here. So it currently, just watch this as I change the length of the sides. So it is currently less than, and then when I drag this vertice to make it an acute triangle, there's the swap, or the switch, the swap, if you will. So now we see that we're dealing with an acute triangle. Notice the definition of acute triangle is all three angles less than 90 degrees. So in fact, this angle here being 86.779 degrees, not much less than 90, but we see that a squared plus b squared is greater than c squared. So we can continue to manipulate the sides as you will. Make sure we're playing around with an acute triangle. So notice that the length of this side squared plus the length of this side squared. Now, again, it's not the hypotenuse, so we really have to focus on the two shorter sides squared and added together. These two shorter sides squared and added together is still greater than our longest side squared. So what happens if a squared plus b squared is greater than c squared? We're dealing with an acute triangle. So now let's jump back over and continue playing around with it. You can't mess it up. You can also reset it if you want by clicking this little icon in the top right. So if you want to go back to that 3, 4, 5 and continue playing around with it, but let's go and add our information to our book. So if a squared plus b squared is greater than c squared, we are dealing with an acute triangle. And if a squared plus b squared is less than c squared, we are dealing with an obtuse triangle. So again, the definition of acute triangle is where all three angles measure less than 90 degrees. And the definition of obtuse triangle is where one angle is greater than 90 degrees. And of course, the definition of right triangle is where one angle is 90 degrees. So I've added the definitions here. An acute triangle is in a triangle that has all three angles that measure less than 90 degrees, and an obtuse triangle in a triangle where one angle is greater than 90 degrees. So think about the usefulness that the Pythagorean theorem provides. Not only if it's a right triangle can we find the length of a side of that right triangle, but it also can tell us if it's not a right triangle, what type of triangle is it? So I do want to stress here again, and these are referred to as inequalities, those that are going back and looking at your learning targets. We cannot use the Pythagorean theorem as it is to find the length of sides of triangles other than a right triangle. When it's not a right triangle, we can actually determine what type of triangle it is using the Pythagorean theorem. So let's just make that very clear here. We will not use the Pythagorean theorem to find the length of a side of an acute triangle or an obtuse. We're just using it to determine if it is acute or obtuse or in fact a right triangle. So if you would, go ahead and draw a line at the bottom of the page. We are going to chunk items 5 and 6 together. So attempt item 5 and 6 before playing through. Okay, so the idea is simple. We're going to use the Pythagorean theorem to determine if it's a right triangle, obtuse, or an acute triangle. Now, the length of the legs or the triples that they gave us here might have thrown you off a little bit, but the goal is simple. Determine if it's acute, right, or obtuse. So I want to stress that you don't always use the first number for A, the second number for B, and the third number for C, although that tends to work well here. In the Pythagorean theorem, C is your longest side, known as the hypotenuse. So be sure when plugging in for C, you're using your largest measure, because that would be the hypotenuse. So 12 squared plus 34 squared, does it equal 37 squared? Well, I found out that A squared plus B squared is actually less than C squared, so it is obtuse. This one might have given you a little trouble, but squaring a fraction is very, very simple. 6 over 7 squared is just the same as 6 over 7 times 6 over 7. So when multiplying fractions, you multiply across. So we get 6 times 6, which is 36, 7 times 7, which is 49. So really, if you think about it, 6, 7 squared, you just square both the numerator and the denominator. So 6 squared is 36, 7 squared is 49. So we see that 36 over 49 plus 64 over 49, because that's 8/7 squared, we do get 100 over 49 equal to 100 over 49. So it is a right triangle. The last one we have here on item 5C is 20 squared plus the square root of 42 squared equal to 21 squared. So I definitely want to show you why the square root of 42 squared is just 42. So if in the Pythagorean theorem, for example, we have c squared equals 49, you might know what c squared, or you might know what c is, because you know what the square root of 49 is. But to solve for c, we take the square root. Because taking the square root and squaring a number are undoing operations. Just like to undo addition, we subtract, to undo multiplication, we divide. So these are undoing operations. So look what we have here, square root of 42 squared. Well, squaring the square root of 42 undoes the square root, and we are left with 42. So the square root of 42 squared is 42. So we get 400 plus 42. Well, it definitely doesn't equal 21 squared, 441. So the sum of our two legs squared is actually greater than our hypotenuse squared. So this is an acute triangle. Last and certainly not least, Sarah's best customer wants to design a kite in the shape of a triangle with side lengths 27, 34, and 45. Classify the triangle. So just using an example from the text to classify the triangle. So again, the reason I use 27 and 34 as A and B is because they are two shortest sides. 27 squared plus 34 squared doesn't actually equal 45 squared. But these two together added is less than c squared, therefore it is obtuse. The last thing I want to point out, because we are determining if they are acute, right, or obtuse triangles, is something that we should mention back up here next to the math tip. In order for it to be a triangle, notice what it says, to create a triangle, the sum of the lengths of any two sides must be greater than the length of the third side. So the sum of the lengths, not the sum of the squares, but the sum of the lengths of any two sides must be greater than the length of the third side. So look here, for example, we'll actually use this chart for that information because that's an important geometric relationship. 5 plus 12 is 17, which is greater than 13. 13 plus 12, 25, definitely greater than 5. So this does, in fact, make a triangle. However, notice it said that it had to be greater than the length of the third side. These two shorter sides added together, 6 plus 6 is 12, not greater than 12. So a triangle can actually exist if two sides are 6 and one side is 12. Think about it. If we have one side that's 12 inches long, how would the two 6-inch sides touch? Well, if we started here, that 6-inch side couldn't have any angle to it whatsoever because it would have to lay perfectly flat to meet end to end because 6 and 6 is 12. So it wouldn't make a triangle at all. So consider it that way. 5 and 6, we have 5 and 6 together is 11. So if 6, 6, and 12 didn't work, 5, 6, and 12 certainly doesn't work. And again, we're not saying they're not right triangles. We're not saying they're not acute triangles, not obtuse. We're saying they're not triangles at all. This next one, 5, 12, 15. Well, 5 and 12 is 17, so that checks out. It's greater than 15. Again, 5 and 12 is 17, definitely greater than 12, so that checks out. 6, 12 is 18, definitely greater than 13, so that checks out. And 6 and 12 is 18, which is definitely greater than 15, so that checks out. So just a nice review of a geometric property you might have forgotten about from middle school to actually determine if it can make a triangle at all. So if it can't make a triangle at all, then it definitely can't make a right, acute, or obtuse triangle. So I think that's important that we mention as we close out lesson 20-2. So as always, at the end of our lessons, be sure to go back to the learning targets. Evaluate your understanding now that you've watched the video. If there's any parts of the video that didn't make sense the first time, of course, watch those over and over again. And as always, complete the lesson practice to help solidify your understanding of lesson 20-2. Thank y'all for watching.